Um, okay, maybe let me do an extra page. So we mentioned there are three transistor configurations. The one that we use the most frequently is a common source amplifier. And we talk about a common gate amplifier where the here is applied to here is a DC bias, and here is current source bias, and this is where the signal actually is fed here. So this is a common gate. This is what we talked about last time. Okay, and we learned a few things. Basically, the current gain, this is really a current device. The current gain is -1. Whatever flows through here has to flow basically through here as well. And we learned that the voltage gain is actually similar to the common source amplifier. The common source, the voltage gain is -GM RD, okay? And here is positive GM RD, okay? So they share some commonalities. We fed the input, so here is V in is here. Here V in is here, V out is here, okay? Here V out is here. So by kind of choosing to put our input at a different place, we could get different results. In this case, the voltage gain is the same, but the input resistance and output resistance is very different. The input resistance, R in here, is now very small. We look into the drain. So we will practice this more. We look into the drain. The input resistance is very small, 1/GM, whereas here the input we're looking into the gate. Gate is basically an open circuit. So R in here is infinity. And R out here, okay, the R out here of the whole amplifier is basically equal to R0 in parallel with RD. So after we finish the discussion of the next circuit, I will explain more sort of the intuitive way of inspecting the circuit. The R out here in the... is that better? Okay. So this R out is really large. It's basically GM R0, and assuming we have RS, assuming actually we have RS here, okay. If this is a voltage source, then RS is here, RS. So this is GM R0, small r0 times RS. So this is really big. This is reasonably big, but the common gate output resistance is really big. So today we're going to talk about the third configuration, where is a common drain. So drain is now common here, and input still fed in from the gate. Okay, and output goes here, and normally this transistor still needs bias. So we assume, we have a current source bias. We can have a resistor bias, but let's assume ideal case we have a current source bias. So that's the topic for today. Another configuration that are very similar to the common source is a common source with degeneration. So common source with source degeneration. So if you have RS here, RD, and this is your input. So this is very similar to your lab 5 components that you have a common source with source degeneration. Okay, and you hopefully have learned from your lab or see hands-on the effect of this RS. It actually, this provides a negative feedback capacitance. So this stabilize your biasing circuit. Stabilize basically ID, and therefore it stabilize GM and stabilize all your circuit parameter. A very simple intuitive explanation for that is, this circuit set up a current ID, right? And ID set up all the small signal parameter, basically GM. ID is equal to the voltage drop here, VGS, okay? So imagine if ID somehow is influenced by temperature, as in the example of the lab we want you to investigate. Let's say temperature change, ID change. Let's say ID, for example, try to increase. As ID increase, now VGS, which is equal to VG minus ID times RS here, and because ID increase, VGS will decrease. So VGS actually decrease. As VGS decrease, ID is equal to basically 1/2 Kn VGS minus VTN square. So as VGS go down, this will force ID to go down. So you see the negative feedback process. As current try to deviate from your design value, the presence of RS help pull it back. Okay, you do pay a price for that. The gain is smaller. Okay, if we have time today, we'll talk about that. But the gain, instead of GM RD, it's actually going to be 1 plus GM RS. So your gain, you pay a price, but the price is well worth it. So we do this trick all the time. But let's return to this common drain here for the main topic today. All right? Okay. So common drain amplifier. So it's shown here. We need a bias circuit. So first of all, when we set up amplifier, we set up in the right configuration. Common drain here, drain is connected to the most positive power supply, VDD. It's AC ground, but the DC wise, it's most positive voltage. And we need to set up the gate. So we have a bias, DC bias voltage. We have AC here, so this is DC. We have AC, and there's a source resistance that's usually accompanied by whatever source we feed it to it. We need to bias the transistor. The most important bias is the drain current. Okay, so we bias it with this IQ here. So in this case, current source bias, ID is basically equal to IQ. So that's very straightforward, biasing scheme once we set it up this way. And today we will go into how we actually implement this current source. So once you have this current source, we know IDS. So IDS equal to IQ. And therefore, we know VGS, we know the DC value of VGS here. It's simply related to this equation in the saturation regime. So you inverse that, you can find out what is VGS. So once you know the value of that, you can find out GM. So GM is basically equal to Kn times VGS minus VTN, okay? And so that's your small signal. So we can then convert that to AC small signal. So usually we just, let me get back to this value here. So usually we just first draw on this diagram. For AC, we convert VDD to ground, okay? We convert this DC bias to short circuit and convert the current source into open circuit. So this AC circuit now becomes like that. So it's open circuit here. We still have the load. Here's V out, here's V in, right? And the drain is now grounded. Sometimes when you saw this, you have to remember this is already the AC equivalent circuit. And you know that because otherwise you cannot have current flowing between ground on top and the ground at the bottom. So, you know, this doesn't make sense for DC circuit. This makes sense only for AC circuit, all right? Once you have this AC circuit, you can bring in the hybrid pi model. So the hybrid pi model, you have this dependent current source, GM, VGS, the output resistance RO, okay? And here is drain, here is the source, here is gate. Input is applied to the gate. Output is taken out from the source. Drain is grounded. Okay, so that's the equivalent, small signal equivalent circuit for blown AC equivalent circuit here. Okay, so the rest, once you reach this point, the rest is KCL and KVL. Okay, questions so far? Okay, so we're going to do lots of KCL, KVL experience here. So VGS, first you can write, well, VGS here, this VGS. VGS is basically equal to V in, VG is equal to V in, and VS is equal to V out. So it's V in minus V out. Okay? And you can do KCL here at this node. So KCL at source. So here is V out, and so the current coming into the node, that's GM VGS, is equal to the current flowing out of this node. So it can flow upward through R0, it can flow downward through RL. So this is equal to V out and 1 over R0 plus 1 over RL. And you substitute this VGS in, so GM V in minus V out equal V out divided by, this is really R0 in parallel with RL. Okay, and you move V out over to the other side, and you will have basically V out divided by V in. So this is your voltage gain. Okay, V out is going to be that's jumping a few steps. So V in here is GM, and here will be GM plus 1 over R0 parallel RL. Okay. So this will be the voltage gain of this circuit, right? Yep, question?
Yeah. Is there any specific reason why you ignored the source resistance?
Yeah, source resistance can always be dealt with once we come up with the two-port model. RS, it's a simple resistor divider. It makes the analysis a little bit easier. Okay, so this is the voltage gain. Okay, so we got this expression. This is the voltage gain. You can rearrange it a little bit. Usually, RO, we say RO is large. This is something like 200 kilo ohm. And RL usually kind of like a 10 kilo ohm, 10 kilo ohm. So this is usually we consider as this is a large resistor. So R0 parallel RL, most of the time it's just equal to RL. Okay, so we simplify this. This is basically just RL. So it will become like GM divided by 1 over RL plus GM. Okay. In this expression, GM RL is kind of a medium. So we consider this as a medium resistance. Medium resistance. Okay, these are typical value. There's no, it's not fundamental. And so we are comparing RL, 1 over RL with GM, or we are considering basically comparing, so we're basically comparing RL with 1 over GM, okay? Usually we consider 1 over GM as the smallest resistance. Okay, so for most typical examples, we say think of GM, typical value of GM is 500 microsiemens. So 1 over GM is roughly 2 kilo ohm. Okay, so usually we consider RL to be much, much greater than 1 over GM. So whenever we encounter 1 over GM, consider that as a small. So therefore, 1 over RL should be much less than GM. So the inverse of the resistance is the opposite relationship. So in this voltage expression, it's almost 1. It's a GM, so it's always smaller than 1, but almost 1. So these are like 0.9, could be 0.98, depends on the choice of RL. So it is a unity voltage amplifier. So this is the kind of a counterpart of the common gate, which is unity current amplifier. This is unity voltage amplifier. So in other words, it is a voltage buffer. So this is a voltage buffer. It's a unity gain. So this is unity voltage gain. So this is going to be used as a voltage buffer. Okay. Like other configurations, we like to find the input and output resistance. Okay. So to find the output resistance, we put in RS. So the procedure for finding output resistance, we need RS in place. We remove RL. So RL usually we take it out of the equation. So we can take this out of the equation. And we apply a test voltage here. We supply a current. And there's no current flowing through here. So I is equal to 0. And therefore, VG is equal 0 because there's no current flowing through here. Right? So this is voltage is basically grounded. So in this case, VGS here is simply equal to 0 minus Vx, where Vx is the test voltage that we applied here. Okay. And so therefore, we do a KCL here, and we do KCL at the source. So this is source. So KCL at source. And basically, Vx divided by, Ix. So if we take RL out of the equation first, then Ix is equal to minus GM VGS. Okay, the minus sign because this is also coming in to the node. Okay, so I put it on this side, so it's a minus sign. And then we have the current flowing through R0, so we have Vx divided by R0. And we put VGS in, so this will be equal to GM Vx plus Vx divided by R0, okay? And so you can find the R out, okay? R out is equal to, let me use R out prime because this doesn't have RL. So this is equal to Vx divided by Ix, and this is equal to basically 1, and here is Gm plus 1 over R0, okay? Now think of 1 over Gm as a resistance. So this is actually equal to 1 over Gm in parallel with R0. Okay, if you want to verify it, so let me work backwards. So this is 1 over Gm times R0, 1 over Gm plus R0. That's how you expand the two resistors in parallel. So these are exactly the same expression. So these are exactly the same expression. Okay. So your output resistance is 1 over Gm in parallel with R0, and these are if we consider RL, so the total output resistance, RO, will be 1 over Gm in parallel with R0 in parallel with RL. And as we argued before, R0 is typically much greater than RL, and both are typically much greater than 1 over Gm. So when they are in parallel, it's equal to the smallest resistance. So it's basically 1 over Gm. So we found the output resistance. Input resistance is kind of trivial because we are looking into the gate again. So the full two-port model is therefore shown here. It's unity gain. So we have, this is V in, V out. So this is a two-port voltage amplifier model. So this is a two-port, okay, voltage amplifier model, okay. So here R in is infinity, okay. And here is voltage gain, AV, we said is nearly 1. So this output voltage is exactly equal to the input voltage. This value we put here is R out, okay, R out is 1 over Gm. So this is now the equivalent circuit of the entire circuit, not just the transistor, but the entire circuit. Question?
Is there any cases where the input impedance is not dependent?
Yes. Remember the very last example we talked about, the common gate? The common gate here, this common gate example. The input resistance, input is applied to the source. So input resistance, we look into we look into the source, input resistance is actually very small. So this is the case, input impedance is not infinity. For all other cases, common drain, it is infinity. Common source, infinity. Common source with degeneration, infinity. So there are three cases the input resistance is infinity.
So the input resistance is either really small or really large. It's not like in between.
That's right. That's right. That's right. And usually, you want it to be either very small or very large. If you are, if you have a source, if your input, so this depends on what do you wish. Okay, so what do you wish? We were here. Let me say, let me add a page here. Okay, so if you have, if your signal is a current source, is a current source in nature, okay, and current source we represent it by a current source here, okay, and it has an RS. And if we're going into a two-port network here, right? So this is your R in, right? So when we connect these together, the real current that flows in there that counts is this current. So this I in and this is IS. So I in is equal to basically the inverse resistor dividing. So this is RS plus R in and RS. So you want, in this case, R in to be really as small as possible, right? So if your current source, if your signal source is like that, you would be considering using the common gate. Now, if your signal is voltage in nature, okay, so if you have a voltage source, and then we represent voltage source by something like this. Thevenin equivalent circuit is better to use to describe a source. Again, you have a two-port model here, and you are looking at an R in, okay? And the real voltage gets amplified is the voltage here. So your V in here, and if we call this Vs, your V in is actually equal to your Vs, voltage divider, Rs plus R in, and this is R in. So in this case, you really want your R in to be as large as possible. Okay, so you kind of desire the two extremes. Okay, all right, good. So that kind of brings us to this nice summary of the three amplifiers. And this is the common source, okay, common source. We talk primarily about NMOS configuration, where input goes to the gate, output take from the drain, okay. So the gain here, this is really a voltage amplifier, okay. Well, this is really a transconductance amplifier. It's really a transistor itself. So we use the two-port model. We use the voltage as an input and the current as output for this case. So we have a GM. The GM is just happen to be the GM of the transistor. And the output resistance is RO, okay. ROC means the equivalent resistance of the current source is ROC, okay. If the current source have finite resistance, then we have to consider that. Otherwise, this is just RO. So this is the model for common source amplifier. PMOS will be exactly the same, but you kind of flip the whole thing over. The current source is at the bottom, still connected to the drain. Input still applied to the gate. Output you pull from the drain. Okay. We also talk about this is a common gate. Okay, so this is common gate. It's a current buffer. I here stands for current. So whatever. So here we really thinking of putting I in here. Okay, and we're getting I out here. I in here it's nothing hanging at the input port. That's because we already taken the DC circuit out. So the I in goes into input resistance, 1 over GM, and it goes to current gain, which is -1. So AV is minus AI, not AV. AI is -1. Okay, so here AI -1. And then the output resistance, we said this is a super big output resistance. We would have, if we have RD here, okay. So this output resistance is really super big. We said this is GM times R0 times RS. Whatever source resistance gets amplified here by GMR0. This RD is assuming, well, if we have a resistance here, if this is RD, then it's in parallel with RD. Okay, but it's large. And for current output, you want the output resistance to be large as possible, so that you deliver your signal, your output current to your load rather than being consumed in your internal output resistance. Okay, this is a very last case. It's a common drain. Common drain also often called source follower. So this is equal to common drain. Why is it called source follower? Because the output is a source. It always follows the voltage you apply to the gate. So it's a source follower. It follows the gate, source follower. Voltage gain is 1. So voltage gain is 1. Again, we put it in because we are transforming the resistance. Here we have the source looking at infinity input impedance, and whereas at the output, we have very low output resistance. So we have convert something into, we presented the resistance. We convert something from very large resistance to very small resistance, even though we don't have voltage gain here. So these are all the Lego blocks we have that we're going to all utilize them. We need all 3 of them. We actually need the fourth one. The fourth one is common source with degeneration. Okay, we actively use all 4 of them. Yep.
You said before that R12 over GM is around 2 kilo.
Yeah.
Is that typically a very small resistance?
Yes. For integrated circuits, kilo ohm is kind of a very small resistance. Even in your discrete amplifiers that we are building in the lab now, as you see, your RD is on the order of a few kilo ohm. In this case, they might be comparable, but if you were designing IC chip, usually all other resistance are much bigger. Okay, so any question about the summary? This is kind of a very useful summary. I'm going to kind of give you an intuitive feeling how you look into the terminal. So a FET, okay, here we have an FET. If we look into the gate, okay, so if we look into the gate, usually you see an open gate. So kind of if you think of, this is a loose term, we say we look into the gate. So R looking into the gate is very large, infinity, okay? Now, in other cases, we are kind of, say, looking into the drain. If we look into the drain,